Hello everyone. Today we are going to study about another important concept, which is quantum Hall effect in low dimensional semiconductor structures. So what actually is quantum Hall effect? What are the different features? How the system has to be? How the phenomena takes place? We are going to study in our today's class. Quantum. We know that it is with respect to microscopic scale, or we can say nanoscale. And Hall effect, if you consider a classical Hall effect, we just say that if you consider a current carrying conductor and magnetic field is applied perpendicular to the direction of current flow, then voltage will be developed perpendicular to both magnetic field as well as current. So that is your general Hall effect. So how quantum Hall effect is going to vary with respect to classical Hall effect is what we are going to study today. So first let us understand how this came into picture. So the first experiments exploring quantum Hall effect were performed in the year 1980 by von Klitzing, almost approximately 100 years later after the Edwin Hall discovered classical Hall effect. So classical Hall effect was found out very early, and almost after 100 years quantum Hall effect came into picture. And for his work, von Klitzing was awarded Nobel Prize in the year 1985, just after 5 years of his exploration. And this quantum Hall effect can be divided into two types, or there are two kinds of quantum Hall effect. First one is the integer quantum Hall effect, and second one is fractional quantum Hall effect. So the integer quantum Hall effect is the basic type of quantum Hall effect, whereas fractional quantum Hall effect is little bit complex one. And we are going to discuss about the first one, integer quantum Hall effect, and while studying we will understand what is the difference between these two types of quantum Hall effect. So first let us understand how integer quantum Hall effect system has to be, or what are the criteria for quantum Hall effect to take place. So main thing, there are totally four. So first one, how the system has to be. So the system is a thin two-dimensional or quasi two-dimensional electron gas in which the electrons are restricted to move in two dimension. That is, the motion is confined in a plane, we can say. And if you consider this is your semiconducting material, and we are having the degrees of freedom for this system is equals to 2, that is two-dimensional system, and the carriers can move only along x and y direction, but it is confined to move along z direction. That's why we are having a two-dimensional system here. So if integer quantum Hall effect or in general quantum Hall effect has to take place, means we need a two-dimensional system. And if it becomes three-dimensional, we are going to switch over from quantum Hall effect to classical Hall effect. So this is first criteria for IQHE to take place. Second one is the magnetic field. How the magnetic field has to be. So here we need a strong magnetic field, we can say of the range 5 to 30 Tesla, which is applied perpendicular to the direction of plane, where if you consider this xy is the plane of the semiconducting material, then the magnetic field will be popping outside in the upward direction or in the downward direction of the plane. So this is the nature of magnetic field, which is very important if we need to observe Hall effect. Third point we need to understand is about the condition. So the experiments are conducted at low temperatures so that the quantum effects become more important, and only at low temperature we can actually observe the prominence or dominance of quantum effects. Coming to the fourth point is the disorder, and this disorder is an integral part of this effect and plays an important role, and if this disorder is absent, then we can say that the quantum Hall effect is going to reduce to classical Hall effect. So all these four parameters are very important if we need to know or if we want to understand about quantum Hall effect. Even if one of these is missing, let us say system is becoming three-dimensional, then we are having classical Hall effect. Even if you go for higher temperature, then disorder, it is going to be again disturbed, means again it will be absent. That's why we will get classical Hall effect. So all are interlinked, and all these four parameters which I have underlined, these are the key points which are to be remembered when you understand about quantum Hall effect. Then let us understand how the phenomena is going to take place. So in the above system, we can just say the current is flowing along x direction, which is represented as Jx. So Jx is along x direction, and we are applying magnetic field along z direction perpendicular to the plane of the semiconductor, and that's why the voltage will be developed in transverse direction due to the segregation of charges, and this voltage, whatever we are getting, will be perpendicular to Jx as well as B. So if Jx is along x-axis, B is along, that is magnetic field is along z-axis, then the voltage or the potential will be developed along y-axis, which can be measured using the voltmeter. And why this voltage is developed? Because when the magnetic field is applied for the current carrying conductor or semiconductor, the carriers whichever are present in semiconductor, we have electrons as well as holes as the carriers, and these are going to segregate due to the effect of these two fields. So one part or one edge of the semiconducting material will be saturated or segregated by electrons, whereas the opposite part will be having only holes. So due to this separation, we have the potential difference. That is nothing but the Hall voltage. So this is how the quantum Hall effect takes place. Phenomena is same, current is flowing, magnetic field is applied, and voltage will be produced. Only difference is that the four parameters which we have discussed, that is, system is two-dimensional, strong magnetic field has to be applied, low temperature, and disorder in the system. So the combination of classical Hall effect with this system gives us quantum Hall effect. I hope the picture to visualize is clear. Now let us understand in detail about the changes which is occurring within. So based on this phenomena, there is also resistivity in the direction of the flowing current, that is along Jx, and I am going to represent it as rho xx. So this is the resistivity in the direction of current flow, and current flow is along x direction, and this rho xx is generally called as longitudinal resistivity or also called as magnetoresistance. So in our previous class we have already learnt about magnetoresistance, and also I will mention it in the above suggestion box. You can just observe it in I button. Just understand so that you can link the concept here also. So this rho xx will be denoting the magnetoresistance, and there is another type of resistivity also which will be transverse resistivity based on the direction or configuration of these parameters, and it is also called as Hall resistance or Hall resistivity. So I am telling it as Hall resistance as well as Hall resistivity. So does that mean the resistance and resistivity both are same? So let us understand what happens to resistance and resistivity for two-dimensional case. In general, we have resistance in terms of resistivity as R is equals to rho into L raised to 2 minus D. Rho is resistivity, R is resistance, and L is the dimension of length, raised to 2 minus D, where D is the degrees of freedom. So this is a general formula based on which you can get the relation for resistance as well as resistivity for any type of a system. If you consider a three-dimensional system, then you need to just put in place of D, we have degrees of freedom for three-dimensional system as 3. So 2 minus 3 will be equal to minus 1. That's why based on this we are having the formula R is equals to rho L by A. Whenever we ask the relation between resistance and resistivity, this formula comes in our mind. But whether it is applicable for all the systems? No. It is only applicable for 3D system, and if you just put the dimension of length as well as area, we can say that L is nothing but length, so dimension is L, but area, it will be having the dimension of L square. So 1 L is going to cancel out, and finally we are getting rho L raised to minus 1. That's why for three-dimensional system we can say R is equals to rho L by A. Then if you consider two-dimensional system, then degrees of freedom D will be equal to 2. So if you substitute in our previous formula, we can observe that R is equals to rho. And that's why we say that for a two-dimensional case or two-dimensional system, resistance and resistivity both are acting as same. That's why we can say it as Hall resistance or Hall resistivity. But if you are considering the three-dimensional system, this is not going to work. And this is an important formula based on which you can understand the relation between the two, which is going to help you in competitive exams. So with this knowledge, let us move on to the next concept of resistivity. That is, if you plot the graph of resistivity as a function of magnetic field, what is the nature? So resistivity, we are having two types. One is longitudinal, that is denoted as rho xx, and transverse, it is rho xy. So if you plot the transverse resistivity, it is showing plateau type structures or step like structure, where we have just represented it with lightish pink curve. Whereas if you consider rho xx, that is the longitudinal resistivity, we can observe the nature like peaks. So these peaks, what they are going to represent, let us see. So yellow colored peaks are with respect to rho xx, which is the longitudinal resistivity. So this is in general nature of graph for resistivity as a function of magnetic field when you consider quantum Hall effect. So both Hall resistivity rho xy and longitudinal resistivity rho xx, they are going to exhibit very interesting behavior. So based on some formula, let us understand it. First, if you consider rho xy, they have plateaus at integer multiples of h by e square. That is, it is represented as rho xy is equals to h by e square into 1 by gamma. Let us call it as equation number 1, where this gamma is an integer which is having accuracy of 10 raised to minus 9 units. H is the Planck's constant and E is the charge of the electron, or we can say elementary charge. And this h by e square, the term in the formula equation number 1, is taken as the quantum of resistivity, which is also called as Klitzing constant, having the value of 25.8 kilo ohm. So Klitzing, based on the exploration of this quantum Hall effect, it is in his honor, and this is nothing but the quantum of resistivity, because gamma we can just observe it is an integer 2, 3, 4, 5 so on. And when you take equation number 1 rho xy, we can observe that we are having 1 by gamma times, it may be 1 by 2, 1 by 3 times. So it is a number times that of h by E square. So we say quantum of resistivity, that is h by E square. Then if let us say gamma is equals to 1, then the above formula denotes one quantum of resistivity, and further resistivity can be expressed in terms of the one quantum. And the main difference, if you want to observe, between integer quantum Hall effect and fractional quantum Hall effect is that it is with respect to gamma value. So for integer quantum Hall effect, gamma will be integer numbers, that is 1, 2, 3, 4, 5 and so on, which is already represented in the plateau form. But if you consider fraction quantum Hall effect, there these gamma values are going to be in terms of fractions. So gamma can be 1 by 3, 2 by 5, 3 by 7, 2 by 3, 3 by 5, 1 by 5 and so on. So based on these gamma values, we are going to differentiate between the two kinds of quantum Hall effects. So this is the difference, and whenever we are having the integer forms, easily we can just simplify the further expression, and that's why this integer quantum Hall effect is a basic one and fractional quantum Hall effect is going to be little bit complex. So phenomena is going to be almost same. Main difference is with respect to gamma value, based on which again that quantization and all is going to change. So then coming to the next thing, that is how resistivity is going to change, why this nature is coming. So the center of each plateau occurs as the magnetic field assumes a value B is equals to NH by gamma into E. So plateau we can just observe in the graph denoted by light pink, that is rho xy. So there are step-like structures. So when these steps are going to take place? When B will be equal to NH by gamma into E. So this H by E, N by E can be taken as, sorry, it is H by E. H by E can be taken as phi naught. Just make the correction. So B will be equal to N by gamma into phi naught. So N by gamma is nothing but N is a number, gamma is again an integer. So finally we are getting certain number into phi naught. So this phi naught, which is equals to H by E, is called as flux quantum. That's why at these values the plateau are going to be formed. So there are jumps in the resistivity graph when B value is going to be integral multiple of the flux quantum. So N is the electron density. So it is a number. So these are precisely the values of magnetic field at which gamma number of Landau levels. So Landau levels we have already studied in Fermi surface studies. So these values of magnetic fields which are given as B is equals to N by gamma into phi naught, where the gamma number of Landau levels are filled and the Hall resistivity takes the values as given from equation number 1. So based on the combination of these two equations, we have these graph. So how B is going to change with respect to B, gamma is constant, rho xy is going to change. So the quantization persists over a range of external magnetic field. So this is about rho xy. Then let us understand about rho xx. So this longitudinal resistivity rho xx shows a surprise as it is 0 most of the times, except when there is a jump in rho xy from one plateau to another. We can observe that the peaks in this yellow graph, which represents rho xx, that is longitudinal resistivity, is occurring only when there is a jump in rho xy. So whenever there will be change in the peak, so as the peaks are changing, it is accompanied, that is with respect to jumps in the plateau, we have the peaks in our rho xx, that is longitudinal resistivity graph. So what is the importance of this? So when rho xs is equals to 0, that is longitudinal resistivity is 0, it means it is a perfect metal or a conductor. So here in the yellow graph we can observe there are certain peaks, and otherwise it is going to be same as that of the x-axis, means it is equals to 0. So when rho xx is equals to 0, it means resistivity is 0. And whenever resistivity is 0, its reciprocal, which gives us conductivity, is maximum, or we can say infinity. And that is the case for a perfect metal or a perfect conductor. That's why when this longitudinal resistivity is 0, we can say that our semiconductor or the system, which is two-dimensional in nature, acts as a perfect metal. Whereas if you consider where the peaks are present in this graph, that is rho xx is not equal to 0, in that case we say the material is acting as an insulator, because here there is some amount of resistance or resistivity present in the material, and whenever resistivity is there, it is a opposition to flow of current, means it is not acting as a metal, we can just say it is acting as an insulator, because resistivity is very high, which is shown with a very sharp peak. And based on this we can say the system, that is a two-dimensional system, is undergoing a series of transitions from insulator to metal, metal to insulator, and so on. So whenever there is peak, it is acting as an insulator, whereas when it is stagnant, that is when resistivity is equals to 0, it is acting as a metal. So that is going on changing or switching in case of two-dimensional system, when we have current, magnetic field perpendicular to each other, due to which voltage is produced perpendicular to both the directions. So what is the significance of studying this quantum Hall effect is the question. So main application of quantum Hall effect is that it provides extremely precise and independent determination of fine structure constant, which is a quantity of fundamental importance in quantum electrodynamics. So quantum electrodynamics again is a very vast topic, and fine structure constant is a very important term when you go to study about quantum electrodynamics, and the precise determination of that constant can be done using this quantum Hall effect. That's why understanding about quantum Hall effect becomes very important when you consider the quantum effects or with respect to low dimensional system. So this is about quantum Hall effect, and in our next class we will be starting with thin film physics. Till then, study well. Thank you.